Now we're going to move on to a concept that some people have a little bit of difficulty understanding, and this is the non-conservative forces. Remember that previously we had the conservative forces, but now let's talk about non-conservative forces. Now, compare the two systems shown, A and B. System A represents a conservative force, and system B represents non-conservative forces and the effect they have on the mechanical energy in a system. What you notice here is you start out with this rock that falls, and the potential energy of this rock, let's pretend that this spring is at rest, so it has no energy at this point. It falls and transfers all of its potential energy into elastic potential energy. And so the potential energy from the gravity is then equal to the potential energy of the spring. The spring then fires this sucker back up in the air, at which point, because it has a velocity here, it has both kinetic energy, because it hasn't reached the same point. It has kinetic energy still. If it reached this same point, it would be stopped, and it wouldn't have any. It would be the same here. But it's still moving because it's not quite as high. So it has some velocity left, so it has some kinetic energy, and it also has potential energy, which has been transferred again, but it's different, which is represented by prime, and this is the sum of these two. Okay, so this is all the conservative situation, and that's what's stated right here. When the rock is dropped onto the spring, the mechanical energy remains constant, neglecting air resistance, because the force on the spring is conserved. The spring can then propel the rock back up to its original height, where it again is only potential energy. This is not its original height. It's a little short of that, which is why it still has a little kinetic energy. Now this system represents non-conservative force. So the rock falls to the ground, plop, and there's no mechanical energy or potential energy. So what happens is, as this says, if the system has non-conservative forces, then the same rock is dropped onto the ground and it is stopped by non-conservative forces that dissipate its mechanical energy. These forces include the thermal energy that happens, the heat that may be produced, the sound that's produced, the distortion of the surface of the material here. We've talked about that. And the rock has lost its mechanical energy, but it's lost it in a way that you can't necessarily detect. So that's what's meant by non-conservative forces. Now remember the work energy theorem we worked with before. Here's a guy pushing something up an inclined plane. The force parallel is that part that's parallel to the displacement, and it's acted upon by gravity. The work energy theorem, we said before, is the net work on a system, and it's equal to the change in kinetic energy of this system. So the net work equals the sum of the work on non-conservative forces as well as the work by conservative forces on conservative forces. So if there's both of these present, then the net work that's performed has to be done on both of these forces. So for example, here's a conservative force, but here, if this is, for example, generates, the friction here generates heat, that would be a non-conservative force that would take away from it. So the net work is equal to the work done against non-conservative forces plus the work done against conservative forces. And that net work has to be equal to the change in kinetic energy. So the work done by conservative forces is the change in potential energy here. So the non-conservative forces is equal to the change in kinetic energy plus the change in potential energy, or the initial kinetic and potential energy plus this non-conservative force factor has to equal the final potential energy and the final kinetic energy. So a person pushes a crate up a ramp. He does work on the crate. The friction and gravitational force also do work on the crate. Both of these forces oppose the person's push. As the crate is pushed up the ramp, it gains mechanical energy, implying that the work done by the person is greater than the work done by the friction force. Here's another example. We've got a guy sliding. His displacement is this way. He is being resisted as he slides on the ground here by a friction force of 450 newtons. A baseball player whose mass is 65 kilos slides to a stop on level ground. If the initial speed is 6 meters per second squared, what is the stopping distance? The friction force is this number right here. The baseball player slides to a stop in a distance d. In the process, friction removes the player's kinetic energy by doing an amount of work, Fd, where little f here is the frictional force, equal to the initial kinetic energy. Now remember, the initial kinetic energy is going to be equal to 1/2 times the mass times this velocity squared. So 1/2 times the mass times the velocity squared minus this friction force times the distance has to equal 0. So Fd has to equal 1/2 mv squared, and d has to equal mv squared divided by 2f. Put all those numbers in, which we've done right here, and you get 2.6 meters. That's the distance over which the person slides. So you can use this work theorem to figure out the distance that this person will slide before they stop. Now let's talk about a different concept, the concept of efficiency. Efficiency is known as the useful energy output as a percentage of the total energy output. So everything that we do has useful energy, that is energy that actually accomplishes what we want to accomplish. But then there's a total, which is always greater than the useful. And the difference between those two in a percentage situation is known as the efficiency. It's the work output, it's what we accomplish divided by the total energy input times 100. Let's finish up by talking about the concept of power. Power introduces the idea of time. Power is the rate at which work is performed. So it is work divided by delta t, or a change in time. So power equals work divided by the time over which the work is done. I called it delta t because you start at time 0. If you start at time 0, then delta t is equal to t. So here's a girl. She starts down at the bottom of these stairs. She has a certain weight. She has no velocity starting. The normal is equal to her weight, opposite of her weight. And she climbs these stairs, achieving both a final velocity and a change in height. So she has both a kinetic energy and a potential energy. Now she does that over a period of time, and you can use that to figure out what the work is. This W, by the way, is not work, it's weight. What is the power output of a 60 kilogram woman who runs up a 3 meter high flight of stairs in 3.5 seconds, starting from rest but achieving a final velocity or speed of 2 meters per second squared? So she climbs this 3 meters, h here is 3 meters. So you have a potential energy change, you have a kinetic energy change, So you have to use both of those in order to calculate the total, and the time that she does it is 3.5 seconds. So the work that's performed is equal to the sum of the potential energy that she achieves and the kinetic energy she achieves. Now, because she starts from rest, you don't have to take into account the initial kinetic energy. So you just use her final kinetic energy plus the gravitational potential energy, which is these two formulas right here. And you know both the m and the v squared as well as the h here. So you put all those numbers in, which is all of this factor right here. And then remember that power is equal to work divided by time. And so you do all of this divided by the time in which she did it. So here is 0.5 times 60 times 2 squared. So that's a half times her mass times the final velocity squared plus her mass times gravity times h, which is 3 meters. You add all of that up and you divide it by 3.5 seconds, so you get 538 joules per second. And a joule per second is also known as a watt. Humans convert food into energy and perform work, as well as, and much of that work is non-conservative, by the way, as well as generating thermal energy and storing fat. So energy is consumed by humans and it is converted to work, thermal energy, and stored fat. By far the greatest fraction goes to thermal energy, although the fraction varies depending on the type of physical activity. This is just a graph looking at the gross domestic product and on the y-axis and the kilowatt hours of power used per capita of individual. So the larger this number, the more energy that's used. And you see that the higher the per capita income is. This is how much a person makes per person. So what you see is a general trend. As the income increases, the energy use increases and the power use increases, and that's what this is supposed to show. Is you have an increase in GDP, you have an increase in the use of power. Let's do a couple review problems. The first review problem is the following. Calculate the power output in watts of a shot putter who takes 1.2 seconds to accelerate a 7.27 kilogram shot from rest to 14 meters per second squared while raising it 0.8 meters. Now this is very similar to the problem we just did, because you have V0 is 0. So you have the final kinetic energy here and the change in potential energy here, and it's all done over this period of time. BP is equal to work divided by time. So in order to calculate the work, we have to calculate the change in kinetic energy plus the change in potential energy, gravitational potential energy. And this is mgh, and this is 1/2 mv squared. So we need to put our numbers in here. This is 1/2 times 7.27, that's the mass of the shot, times 14 meters per second squared, plus the mass again, 7.27 times 9.8 times 0.8. And that's all divided by 1.2 seconds. Now for the sake of time, so that we don't have to do yet another part, I'm not going to do the math on this, but all you have to do is plug these numbers into your calculator and you'll get the answer here. So let's move on to our next person, who exerts an average horizontal force of 80 newtons with his arm during a 1.8 meter stroke. What is the work output for each stroke? Calculate the power output of his arms if he does 120 strokes per minute. Okay, so essentially we're going to neglect this change in position, so we're not going to take into account that part. We're going to use the more simple formula for work, which is F times D. And we're also not going to worry about the idea that there's a change in theta throughout this. We're going to use this as it says an average horizontal force. So it's the average across here. So what we end up with is work is equal to force, which is 80 times D, which is 1.8. And he does, so it says each stroke, so that would be the work output per each stroke. He does 120 strokes per minute, so his power output is going to equal 120 times the work output for each stroke divided by 60 seconds, or for 1 minute. So this would be the answer to the first part, and this will be the answer to the second part.